Let's add a little bit more detail in terms of the evolution of these transient features. So we can do these kind of transient composites going from the maximum convection day being day 0 to 3 days before, 2 days before, and then 1 day, 2 days, and 3 days after the maximum convection, which corresponds to these states we looked at where the divergence and the absolute verticities show this positive and negative, so convective and non-convective phases, which is what you will see here as well. So looking at composites 3 days before convection, so you can see the time scales here. The 4 to 8 day time scale we picked is not random. These are obviously based on observations as we talked about before. So there are different time scales in different bands of the ITCZ as well, as it's obvious by now. So this is again the Eastern Pacific. So obviously the ITCZ is around 5 to 10 knot depending on the season. So this is just a composite showing that there is subsidence, colder, drier air from above being brought down, and showing relative humidity is negative relative to the lower frequencies, and there are these cells that correspond, which in the southern hemisphere go all the way to 30 south, and in the northern hemisphere all the way to 30 north. So you have this cell here and this cell here. So remember, there is the Hadley cell, which is the mean meridional circulation, which always has rising motion in the tropics and divergence in the upper atmosphere and sinking in the subtropics. We are talking about transients within that. Okay, so within the mean kind of circulation, mean is basically averaging over time. So that mean is made up of these transients at high frequencies, like 4 to 8 day time scales, which is what we are looking at. So you can see the change happening already by day 2. The circulation is changing and humidity begins to build up with the upward motion beginning to happen by day -1. So very rapid evolution. And now you see more of a Hadley cell structure that we are used to, and by the time you reach the peak deep convection, the humidity is fully loaded in the free troposphere, and the circulation is well set up as we expect. And then by day +1 there is beginning to be the breakdown and the secondary circulation and the vertical, complex vertical structure that we looked at before, and there is still some humidity and convective activity left, but you can see that there is a complex circulation. It's not a systematic upward deep convection that we expect here. So by day 2 and day 3, the system has gone back to where we started with. So these are composites of anomalous circulation in the height latitude plane, averaged between 120 west and 110 west. So the labeling is consistently wrong between here and the caption and the labels on the figure itself. Okay, so these are constructed from the 4 to 8 day bandpass filtered fields. Only then will you get these evolutions at high frequencies. Day 0 of the composite is defined as days in which delta OLR is less than 20 watts per meter squared at 7.5 north in the mass stream in the 4 to 8 day band. A total of 40 day zeros were defined in June to September. So that's how many 4 to 8 day cycles you had during 1981 to 2000. So taking all the years from June to September, that's how many events you got. Okay, so again, confirming that there are transients in the ITCZ, which is also seen in the same longitude band in terms of divergence and meridional wind anomaly. So you have day -3 divergent winds and convergent winds, lower troposphere, upper troposphere. So convergence and divergence, which is getting set up, -2, -1, and by the time you reach the peak convection in the 4 to 8 day oscillation, you have well set up convergence and the convergence divergence doublet that we talked about. So you have now the setup of the winds that are crossing the equator, approaching the zero absolute verticity line and going across into the ITCZ or the convection. So they are diverging, and then there is convergence on the other side that we talked about before. And of course the opposite sign on the upper level, as we know. So Hadley cell or any other time scale, you get similar structures in the lower and upper atmosphere. The transition back is complicated in the vertical, as is the build-up. So you have divergence, convergence, divergence pattern, and then it becomes divergence and then convergence, all set by the time you reach back to day +3. So you're basically going day -3 to day +3. When we say 4 to 8 day, we are looking at 6 days, basically because when you do composites it becomes clearer where these structures come from. So this is the total circulation, just to close up the discussion on the transients and the heating rates. Now instead of the humidity, you look at the heating rates, the theta dot that we had talked about. Oops. So high latitude sections, height latitude sections of the total, so it's mean plus anomaly. We are not doing any bandpass filtering of the mass stream function circulations and corresponding height latitude sections of material tendency of potential temperatures in Kelvin per day. Okay, so d theta dt or theta dot, as we have been writing it in terms of diabatic heating rate. Okay, gray shading represents positive heating values are shown. So the heating rates are 5K per day, which is significant. So there is the zero absolute verticity line at day -2, already has crossed the equator and set up the inertial instability. So you have the vertical motion when you see in the total instead of the anomaly. You have to get used to the idea. You are looking for bandpass filtered anomalies at 4 to 8 day time scale, whereas here you are looking at the total, so they look different. So you have to be very clear about understanding that. Okay, but remember the basics, that cross-equatorial advection of the zero absolute verticity line creates inertial instabilities, and we expect heating rates, diabatic heating rates, to respond to those inertial instabilities, which is the main goal, and set up secondary circulations and convection to remove the instabilities. Day 0, you have strong heating rates penetrating deep into the upper atmosphere, and a strong cells being set up on either side with the rising motion over to the north of the zero absolute verticity line. Okay, so day +2, things begin to break down, and if you look at heating rate, day -2, there is a very strong heating rate setup. Day 0, obviously it's corresponding to this, which is very strong as well, and then it begins to break down by day +2. Okay, basically confirming what we have already talked about, and this is another way to look at the evolution in terms of height versus time. Again, 0 day being the OLR based convection time period. We are looking at the southern cold tongue region, not much happening, right, as you expect. But if you look at the eastern Pacific in the northern hemisphere, where the convection is strong, then you have several days before mid-tropospheric heating getting set up with the secondary heating at a lower level, and the heating then gets organized, penetrates deep into the troposphere, which then begins to break down after the deep convection is gone. So within the rain bands we are looking at, there are all these propagating features and transient features of 4 to 8 days, which is the main time period that we looked at in the eastern Pacific, and we made the point that the western Pacific is very different. Okay, obviously Indian Ocean is very different, and the Atlantic is also different. So we still haven't explained entire ITCZ, but we are looking at the main processes in terms of cross-equatorial pressure gradient, advection of humidity, relative advection of total absolute vorticity, and inertial instabilities and convective responses. Okay.